and he's a theorist working on B physics, heavy flavor physics, CP violation, and generally kind of BSM physics and neutrino physics. And he's also part of experimental collaborations. So he joined the Bell2 collaboration and also on NOVA and Dune. And today he will be telling us about charming NSI and CP violation in long baseline experiments. Please, over to you.
Good afternoon, all. I hope you can hear me. I'd like to thank Michael for the kind invitation to come here, and also the Dr. for this opportunity. So I'm going to tell about charming non-standard interactions and CP violation in long baseline experiments. Charming has nothing to do with charm, just to clarify, it's just interesting specs. And to explain that NSI means non-standard interactions, and we'll be talking about CP violation in long baseline experiments. So I'll try to give a brief outline. Okay, so I'll give a brief introduction to the subject, and then I'll tell what are the parameters being involved in this kind of analysis. Just to say a brief introduction about CP violation in the neutrino sector. Then what are the possible implications that we'll have whenever the NSI comes into play. And of course, towards the end, I will actually mention some outlook regarding this subject. Okay, the neutrino physics so far, we have three neutral leptons. They are known as three flavors. And we have the flavor eigenstates, which are known as mass eigenstates, which leads to oscillation. And these oscillations have been detected. We have mixing between these flavor states, which leads to the U PMNS matrix, which is the counterpart of CK matrix in the quark sector. We have mass splittings of the neutrinos and mixings. These are not yet very well measured, and we hope in the coming years we'll measure them very precisely. Of course, there are cosmological limits on various aspects of neutrino physics. In particular, we have some hints about the sum of the neutrino mass and about the hierarchy, the mass hierarchy of the neutrino sector. These are some of the unknown things we have in the neutrino physics. As we mentioned that there are only three neutral leptons or three neutrinos. We have more neutrinos beyond the three flavors. Other neutrino or Majorana or Dirac? This is an important question. What is the absolute mass of neutrinos? For the precise measurement of the mixing angles that we need to know. Whether unitarity is a valid argument in neutrino sector or not, that also we need to explore. Are there a sterile neutrino? Of course, they have already hints, but that is very old one. We don't have any new kind of evidence to support the sterile neutrinos, but still the efforts are on. The CP bias, basically, which is actually going to help us to understand the baryon asymmetry of the universe. And this may also help us to understand the mass hierarchy involved in the neutrino sector. Of course, these are problems like origin of neutrino mass and whether we have these non-standard interactions or any other new physics effects coming into play. Do the neutrinos decay, or there is CPT violation or Lorentz invariance violation in this neutrino sector? These are some of the aspects that we are looking into in the neutrino sector. We have evidence from neutrino oscillations. Actually, as you can see that if you see the atmospheric neutrino, for example, we can see in all sectors, but here I'm giving the example of atmospheric neutrinos. You have the ratio of atmosphere, the mu neutrino to the number of electron neutrino, summing up all the neutrino and antineutrino, we should have 2, the ratio roughly equal to 2. And as we said that in the plots that I have shown, these are the plot taken from Professor Kajita's talk somewhere, which published in Japan Academy. You can see that the dotted line corresponds to the all oscillated neutrinos. The first two plot, it is basically with the first one is the electron type SOP-GB event, and then the next one, second plot, that is SOP-GB mu-like events. Then you see that there is a difference between the unoscillated oscillated one, and similarly for the multi-GB also in the next two plots. In the bottom, you can see that there is a data for R. R is actually defined as number of muon type neutrinos divided by number of electron type neutrino, which is produced in the data, divided by Monte Carlo. It should be 1, but what we see is basically not equal to 1, very much less than 1, which is actually plotted shown in the plot, which is roughly equal to, let's say, 0.6. And this actually convoluted for the discovery of neutrino oscillation, which led to the Nobel Prize in neutrino physics. So we are in a three paradigm neutrinos, where you have all these, we have three mass eigenstates. Basically, we consider them basically massive neutrino nu1, nu2, and nu3. And when we have a corresponding UPMNS matrix, as I mentioned at the beginning, this is similar to the CK matrix in the quark sector. We have three mixing angle in the name of theta 1, 2, theta 1, 3, theta 2, 3. And we can write this UPMNS by 3 unitary matrix. And these are written in terms of the mixing angles that I just mentioned, theta 1, 2, theta 2, 3, and theta 1, 3, with one CP violating phase, which is delta, or the Dirac CP phase delta, which will give rise to the CP violation in the neutrino sector as far as standard model is concerned. Of course, theta should not be equal to 0 and pi, that then only we'll see CP violation. And this as you see, hopefully I will have an expression later on. The CP violation is directly proportional to some term which is contains sine of theta 1, 3. And in the earlier days, at least 2 decades back, we used to believe that maybe theta 1, 3 is equal to 0 or very small, so that we will not be able to see the effect of CP violation. But with the results coming from Diabe and other reactor experiments, that we know that theta 1, 3 is actually non-zero. So that brings us the possibility that we can actually measure the CP violation in the neutrino sector. And of course, we'll be actually dealing with the neutrino beams, basically from the whatever I'm going to talk about is based on the accelerator-based neutrinos, which are actually produced mostly at KK or at Formula. These are the two experiments I'll be focusing on. This is a BG table which actually gives the latest results in the form of NewFit 2022. And I'm not going to the details of it, but we have used most of the data which are there in this table. But this summarizes in this next page. I have given some saline features that I extracted from the previous page. This best fit value of theta 2, 3 is actually coming into the second quadrant. That means it is greater than 45 degree. That is a question basically whether this angle should be plus more than 45 or it will be less than 45. So that we don't know. But at least from the best fit value that we have right now, it actually comes in the second quadrant. From the results that I saw in the previous page, actually there is a preference for normal ordering. I will actually define what is the normal ordering the next page. So we have now indication for the preference for normal ordering, and of course Dirac CP that I mentioned, the one of the CP violating phase that I mentioned in the UPMNS matrix. Of course, sorry, that is the only CP violating phase in the UPMNS matrix that is actually not equal to 90 degree. Okay, so either it can go either plus or minus. That we'll see. Nature will dictate us something. So neutrino oscillations, as we know, these are not sensitive to Majorana phases, and it's also not sensitive to the absolute mass. It actually will have the mass from the probability. We'll see that actually it depends on the difference of the mass pairs. And of course, we have to actually this theta 1, 3 and theta 1, 2 are actually measured with less uncertainty. Okay, so to say that we have the problem at hand right now, beyond we look for anything new in the neutrino physics. Of course, there are many other things, and many new physics that we are looking at neutrino physics. Just to stress that neutrino also is the first like sector where new physics was indicated when we actually saw neutrino oscillation. So we have to determine octet degeneracy. And then we have to have what is the mass ordering and the CP violation. These are the most important things that we are looking at in the neutrino sector. And also we should come to know more about the sterile neutrino in the coming decades. So we'll not go into all the aspects of, there are various BSM things involved, so I will not go into all aspects of it. Let me go to the basics that I'm going to tell. Okay, just to move ahead, these are the experiments that we have right now. Currently, we have one experiment at KK, what is called the T2K experiment. And the next generation experiment corresponding to T2K will be T2 hyperkamekande. So that will be the new experiment, which hopefully will take data in next few years. We have results from Juno and Diabei from China. These are the reactor-based experiment, which actually gave us a very good hint about the theta-1,3 value. That is more or less precisely measured. We still expect more precision in the coming years. INO is the India-based neutrino observatory, which is not yet run. Hopefully, in the coming years, we'll see neutrino observatory in India. IceCube, we are having a lot of data, which is in the pole. Then in the left-hand side, you can see there is NOVA, which is the experiment at Formula, which is currently running. Then the next generation experiment at Formula will be Dune, which is again, it will be similar to T2SK. So we'll be focusing more or less the accelerator-based experiment that I mentioned at the beginning. So I'll take the current experiment, which is T2K and NOVA, and we'll try to predict what we can see in T2HK and Dune. These are the next generation experiment corresponding to T2K and NOVA. Of course, ORCA is also going to have more data. Okay, so to prove physics beyond the standard model, we have to see the effect of this new physics in the oscillation experiment. As I mentioned, there are non-standard interactions, sterile neutrinos, non-unitarity, CPT violation, orange invariant violation, long-range force, etc., etc. These are some of the possible new beyond the standard model physics that you are going to see in the neutrino sector. The subleading effects we need to identify and then see what kind of precision, what kind of, to what extent it will affect the precision physics. And yeah, so we have to constrain this new physics parameter space to see anything new at this level. Okay, let me just go to. So as I mentioned at the beginning, the neutrinos oscillates from one flavor to another flavor, and this UPMNS matrix is given by U23 and U13 and U12. And conventionally, as I mentioned, that theta is the CP validating parameter in the neutrino sector, which is actually encoded in U13. Okay, bit of CP validation from the quark sector, just to give a perspective why we need this and why it is so important. So this is what actually the one is you have electron type neutrino, muon type neutrino, and tau type neutrino. These are related to the three mass eigenstates nu1, nu2, and nu3 by the UPMNS matrix, and the delta CP is the direct type CP validation. If you look at, you compare the quark sector and want to find out what is the corresponding CP validation, which is basically measured by something called Jarlskog invariant. So this expression basically contains, this is proportional to various mixing angles and sign of delta CP, including sign 1, which actually I mentioned at the beginning that if sine theta-1,3 is roughly equal to 0, then we will not able to see any CP validation. But since I'm talking of the quark sector, which is very well known, and we also know more or less what is the CP validating parameter delta CP in the quark sector. And if you put the value equal to roughly 70 degree, what we find is that Jarlskog invariant JCKM in the quark sector is something like 3 into 10 to the power minus 5. And this is not going to help explain the baryon asymmetry of the universe. That is why we also need that from the leptonic sector, we should have CP validation. Maybe we also need some additional source of CP validation beyond what we can get from this standard CP validation. That is why our objective is to first find the CP validation in the neutrino sector. So if we use the same Jarlskog parameter and let's say maximum CP validation, which is let's say theta or delta equal to pi by 2, then what we can get is something like 0. Jarlskog invariant in the neutrino sector will be something like 0.2 0.034, which is at least 2 to 3 orders of extra than the quark sector. So this is a very big point, and we need to actually determine this CP violation so that it will be one of the important aspects to explain the baryon asymmetry of the universe. So how do we do that? The CP violation can be measured in oscillation experiment. We can start with one flavor of neutrino. As we know that the one flavor of neutrino will go to another flavor of neutrino. There will be oscillation. Let's start with flavor alpha, and it goes to new flavor beta. So the probability between new alpha and new beta we measure, and then we also measure the corresponding anti-neutrino probability. And if they do not match with each other, then I will not go into the CP violation basic aspects here. So if these two do not agree, then there is CP violation. Okay, just since we are actually focusing, as I mentioned at the beginning, we'll be actually focusing on the accelerator-based neutrino production or neutrino experiment. So mostly we have the muon neutrinos are produced in the acceleration. So we'll actually look into the probability of muon type neutrino going to the electron type neutrino. And just at the below, I have given a probability expression. This is for the two neutrino case. Of course, 3 neutrino will be a little bit complicated, will come later. But the simplest one is like nu alpha to nu beta. The probability is sine square 2 theta. Theta is the mixing angle, and sine square of 1.27 delta m square L over E nu. Just to mention that if mass is 0, obviously this term will be 0, and you will not be able to see any the neutrino oscillation. And similarly, L is the length, which is the distance between the source of production of neutrino and the place where it is detected. So that is L. And of course, E is E nu is the corresponding energy of the neutrinos. Before moving ahead, just as I promised at the beginning, this is what the mass ordering is all about. We have delta M1 2 square is very well known, and it is positive. So that's what we know which one is nu2 is greater than nu1. But the atmospheric sector is not, the modulus is known, but we don't know basically. So the sign is not known whether nu1 is greater or nu3 is greater. Depending upon that, we have two hierarchy. One could be the normal one, which is like M1 is the lightest, then M2 and M3 and so on. So this is the normal hierarchy, and the other one is basically M3 is the lightest, then M1 and M2, that would be the inverted hierarchy. So this is the biggest, this is one of the questions that we need to address in the neutrino sector, and we'll come to know more about this as we progress. Okay, a bit of these experimental details that we have with the various experiments. So here we have actually compared two experiments side by side. One is NOVA, and the corresponding, the modified one or the latest, which one is coming up is the TUNE experiment. To look at NOVA, it is actually detects neutrino in formula of NUME beam. It is like 14 millirad of X, and the beam peak energy is roughly 2 GeV. We have a active neutrino, active liquid scintillator oscillator actually, or calorimeter for the detection in the NOVA experiment. And the baseline is something like 810 kilometers. So the beam is produced at Fermilab, and it is actually detected at Aas River. So distance is something like 810 kilometers. We have two detectors. One is the near detector, which is small 1.3 kiloton, and the far detector is 14 kiloton. Similarly, when we have DONE in place, which is supposed to come up in few years, so we have the planning is that there will be 40 kiloton liquid argon calorimeter. Here, basically, the detector will be replaced by, say, the content of the detector will be replaced by liquid argon. And then the baseline is 1300 kilometers, and the far detector will be South Dakota. Similar to NOVA and DUNE, we have the running experiment T2K at J-Park in Japan. So we have here the axis, the beam axis is 43 millirad of axis, and the peak energy of neutrinos in T2K is something like 0.6 GeV. The detector is water Cherenkov detector, and the baseline is simply 295 kilometers. Here also we have two detectors. One is the near detector, and the other one is far detector, which is 295 kilometers apart. Similarly, the for Kamiokande detector will be at the same place where we have right now Kamiokande detector, but it will be much bigger. We'll have 187 kiloton third generation water Cherenkov detector. So hopefully all these new experiments will give us more precise values as far as the neutrino sector is concerned. So let's come to the aspect of looking new physics in this kind of neutrino oscillation experiments. Now, as we progress, I want to stress it that the main difference between T2K and NOVA and when we go to DUNE and T2HK is that the baseline will be different. And of course, as we saw, like in the case of T2K and T2HK, the baseline is something like 295 kilometer. But as we go to DUNE, or even to begin with NOVA, we have 810 kilometer, and when you go to DUNE, it will be 1300 kilometer. So apart from the energy, there will be also more effect, a matter effect in the case of DUNE and NOVA in comparison to T2K and T2HK. So, so the matter effect will be certainly stronger in NOVA and DUNE in comparison to T2K and T2HK. So here actually we'll explore the new physics in the form of non-standard neutrino interaction. So to begin with, a couple of years ago, both T2K and NOVA, they actually announced their first result. As far as the CP validating parameter, as I mentioned, that CP validation parameter delta is very important in the electronic sector. So we need to find out this CP validating phase delta CP. But for the NOVA result, actually prefers something like 0.85, the delta CP value, which is here. And T2K prefers something like 1.55. Of course, they are not, we expect them, if it's a standard model CP phase, then obviously it should be more or less same from both the experiments. But we see that there is a huge difference between these two. Of course, there is nothing to worry at this time. It's a very preliminary result. But that actually started the kind of discussion whether there is something new which is happening because of that. Both these experiments, we are supposed to measure the same value, similar value. They are giving very different results. So one of the aspects was basically non-standard interactions. So these are the two sets of people who actually invoked the non-standard interaction to show that whether we can actually match both the results somehow. So as you can see, the green page in the left-hand plot basically is from a NOVA experiment, and the best fit point is something like around 0.85. And the reddish patch was basically from T2K, and this is for normal ordering. Just let me say, the left plot is for standard model and also for normal ordering. Similarly, we also have for the inverted ordering plots. So if you look at this plot, then you see that there is a clearly difference between the two best fit values from the two experiments. One is 0.85 and the other one is 1.55. Now, in the right-hand side, if you invoke the NSI or non-standard interaction, then one can actually see that both of them are more or less giving in the similar result. So that is the summary of these two works. You can see, so one can actually consider the NSI due to the coupling coming from EMU sector or ETAU sector. I'll explain a little bit more later on. So in the below, you can see that in the both the sectors, if you invoke the NSI into it, we can actually explain both the results and both the sectors NOVA and T2K, they match. So these are the 1D plots which are shown. If you can see that in the first row, one can see that the inverted ordering is preferred over the normal ordering if the standard oscillation is considered. But if we look at the downside, basically we see that here the normal ordering is preferred in case the NSI is invoked basically. So that means NSI is playing a like serious role. You can see if without NSI we have a preference of IO over NO. IO means inverted ordering, NO means normal ordering. But the moment we have NSI into it, we include NSI, we see that normal ordering is preferred over inverted ordering. We'll see from our analysis what we are actually getting. Okay, so if you actually, as I said, like if you look at inverted ordering, as such, there is no difference. the difference that I mentioned at the beginning, these two results like Nova gets 0.85, and the T2K gets 1.55. This is only for the normal ordering. But if you go to inverted ordering, there is no serious difference between Nova and T2K. Moreover, both of them are actually giving similar results. Not the same, but similar results. But if you also invoke the NSI in this sector, including EMU sector and ETAU sector, there is hardly any difference. So that means NSI is not playing serious role in the as far as inverted ordering is concerned. This is the conclusion. So let's look at a little bit about the phenomenology that we have included here. So we will consider some kind of a generic like NSI Lagrangian, and we have this. We have fermion, and the neutrino. This is 6-dimensional operator, and you can see that you have a epsilon, which is actually giving the CP violation. Sorry, it is giving the NSI effect. And this is the standard Hamiltonian we have included V. B actually includes the one is defined at the below, one for the matter effect, and all others, the epsilon terms that in the 3x3 matrix that corresponds to the NSI effect. Okay, one can write, as I said, in the two flavor case, we have a probability that I already mentioned. In case of three flavor, it's very complicated, and there are different orders. So the P0 is the standard model, including matter effect. When I go to P1 and P2, these are this P1 corresponds to the NSI coming from EMU sector, and P2 is NSI coming from the ETAU sector. So these are the expressions that we have found, P0 and correspondingly P1 and P2. And we have redefined all these parameters in terms of the definition that I have given. F, G, AKF, delta, and R. R is the different ratio of two mass ordering that we have. Delta M square 2-1 over delta 3-1 square. And similarly, these are the definitions we have used. And so if you consider only the NSI sector from the EMU sector, then we have P0 plus P1. Otherwise, if you are talking of NSI from the ETAU sector, then we consider P0 plus P2, the expression that we have defined. And also, these are the conventions that we have used. We have taken all these epsilons, basically, epsilon EMU, epsilon ETAU, and corresponding the phases coming from the NSI sector. Here, the non-standard interaction can be from production, from the like propagation and detection, but production and detection sector we have ignored. Only the propagation sector we have included, and we actually take the hints from the current results from T2K and Nova, and then try to predict what we can get in the new experiment like T2HK and DU. So if you invoke, if you combine the two data sets from Nova and T2K, and we try to use the formalism that I just mentioned, then try to see what kind of parameters that we can get. And we see that the best fit value in the left-hand side plot, we have epsilon EMU versus delta CP. So we have something like 10% the NSI coefficient that we are getting. In the right-hand side, similarly, we have the epsilon EMU versus the corresponding phase that we have found. This is the parameter space that we get. I have summarized later on in the table. Similarly, if I include the NSI from the ETAU sector, basically, we have the corresponding parameter space, particularly left-hand side is ETAU, and the right-hand side is delta CP. We have less than like around similar to what we got in the ETAU sector, but these are the coefficient that we have taken one at a time, not simultaneously. Similarly, we get the corresponding NSI phase. These are actually summarized here in this table. You have, if you are looking at normal ordering, then we have the epsilon mu is something like 10%, and the corresponding phase, extra phase we have in terms of pi is 0.2. Similarly, epsilon ETAU, and you have epsilon corresponding phase for the epsilon ETAU sector. Inverted ordering also, we have actually found similar numbers. Okay, so let us once we impose these conditions, whatever we found the current experiments Nova and T2K, The left-hand side is basically normal ordering and standard model. You can see that both the sectors are, the plot is basically sin square theta 2, 3 versus delta CP, where both the octants are allowed. As you can see, is both higher octant and lower octant are allowed. But the moment you can, once we invoke the epsilon mu, basically NSI due to epsilon mu, you can see that the higher octant is vanished. We just have the most preference one is coming to the lower octant. So we have actually plotted here in the normal ordering, but we have also done the similar exercise about inverted ordering, which I did show here. Similarly, one can see the same thing for the T2HK sensitivity. As far as standard model and normal ordering is concerned, as you can see, both these things are in the both octants, both more than 0.5 and less than 0.5 are allowed. But as we invoke the NSI from the EMU sector, we can see that the only lower octant is allowed. So somehow the NSI is playing a role. So if tomorrow we measure something, so for sure we need to take into account NSI into effect to clearly say which one is what. So just to make sure that we are doing everything right, we did the one-dimensional plots, and we can see that this the left-hand side is doing normal ordering. We have a very good one-dimensional plot with very low chi-square is preferring here. And if you can see right-hand side, both the red one is basically standard model. You can see both of them, both the octants are allowed. This is chi-square versus sin square theta 2, 3. But the moment NSI is invoked, which is the blue line, you can see that it prefers the lower one. Basically, the upper one is excluded. The same thing we can see for the T2HK. Okay, so here also the first one is, or the lower octant is actually preferred. Similarly, one can actually see the probabilities from nu mu going to nu e for dune, and you can see that interesting probability we have taken to, since we don't know exactly what is the CP violating phase will be. So we have taken some hints, basically minus pi by 2, plus pi by 2, etc. At some point, we have also taken the reference from the new fit that they are also giving some best fit value, and we try to see how the probabilities will differ. We can see that in dune, we can see a clearly distinction between the normal ordering and inverted ordering. So if you measure the probabilities in dune, we can actually see the clear distinction between normal ordering and inverted ordering. Similarly, the moment we invoke the NSI in the right-hand side, we can see still there is some distinction or difference, but still at some point after 2.5 GB, both of them, the delta CP equal to minus pi and pi by 2 will match. But nature will prefer only one CP. So I think the moment we prefer only one value, we can clearly distinguish between the normal ordering and the inverted ordering in dune. The same thing can be done in T2HK, but unfortunately, we cannot see too much of a difference here because of the mass effect here. So we cannot see too much of difference. But still, if we focus only on the lower energy, which is very sensitive to T2HK, there is still a probability that we can actually say something about these two. As I mentioned that in dune and T2HK, we are going to measure the CP violating parameter delta. So if without invoking the NSI in the left-hand side, we have a 6 sigma probability of determining it in the first few years of run, but this is without the NSI. But if you, the moment you see that the NSI is included, we can see that the sensitivity is getting down. So it will be difficult to measure clearly. And one needs to take into account the NSI effect into consideration to clearly say something about that. But in T2HK, it is less affected, as we know that the matter effect will be less. So the NSI effect may be less significant. We can see a little bit better in this case of T2HK. So what we did, we actually tried to look into the CP asymmetries for these two experiments, dune and T2HK. We can left-hand side is various values of NSI that we have taken. Since we don't know what is the exact value of this NSI coefficients, we have taken 0.05, 0.1, and 0.2 up to that. And we can see that looking at the CP violation asymmetry, SCP, which is defined here, and one can see the clear difference. Similarly, for the right hand side plot is for left hand side plot is epsilon E mu, and the right hand side plot is for epsilon E tau. But T2HK, we are not able to see a drastic difference as we saw in the Dune experiment. Coming back to CP asymmetry versus energy, if we plot CP asymmetry versus energy, and the blue one is for normal ordering and the red one is for inverted ordering, one can see clear difference. If you just measure the CP asymmetry, we can see that is including NSI effect, we can see that already there is a clear distinction between the normal ordering and inverted ordering. But in the right hand side, we can see that is the plotted for T2HK experiment. We may not be able to clearly distinguish these two things. So looking at similarly, one can also do the same exercise, CP asymmetry versus delta CP. And the left hand side is for Dune and the right hand side is for T2HK, which you can see that in case of Dune, there is a clear distinction between the normal ordering and the the inverted ordering as far as the CP asymmetry versus delta CP is concerned. But in the case of T2HK, this is there is still some difference, but not as much as we get in case of Dune. So what we did, we actually combined all of them, and then the next exercise what to do. In the earlier case, what we have done, we have taken the NSI coefficients one at a time. Either epsilon E mu is contributing or epsilon E tau is contributing. Then what we did, actually we combined, let both of them contribute simultaneously, and that is these are the plots that I'm going to show. So if you see that the blue one is actually the vacuum effect, and the red one is matter effect, and the green one is the dual NSI. You can see that clear distinction between vacuum and matter effect and dual NSI in the Dune case. And if you look at the right hand side, the first one is left hand side is for normal ordering, and the right hand side is for inverted ordering. In both the orderings, you can see that there is a clear difference between normal ordering and inverted ordering. So hopefully the ACP parameters will give us clear indication in addition to the conventional analysis of delta like mass hierarchy. This parameter also will help us in giving clear indication.
Could I just ask one question to the last slide?
Yes.
So how large will the uncertainties be of Dune in that scenario?
Which uncertainty?
So basically they should have, when they measure ACP, there should be some uncertainty associated to it. How large
at this level, we have not looked into uncertainty. This is the preliminary work.
Yes.
So of course, as I said, like the uncertainty will be there. I mean, what kind of NSI also will affect, that we also don't know right now.
Yes, of course.
So maybe the next round, when the T2K and NOVA are going to announce, this parameter will be more constant.
Yes.
So this was a preliminary result based on which we have taken these inputs. So hopefully in the coming years, we'll have better understanding. Then coming back to the uncertainty in delta CP in Dune and T2K, it is too early to say right now.
Okay, it's not clear yet what they will achieve.
No, not yet. But okay, apart from the uncertainty that we are looking at, we are also looking at the mass hierarchy. So one aspect is, as I said at the beginning, at some point, this is like related to CP violation, delta. But now I'm focusing on assuming some delta, whatever we get, whether we can actually infer something about the mass hierarchy. So that is what these plots are basically for the mass hierarchy. Yes. But yes, uncertainties will contribute here, and they can spoil.
Yeah, that's what I'm wondering.
Yes. But that is not yet.
That's useful.
Okay, so as I said, like T2K also will have similar behavior. So yeah, to maybe I'll just quickly finish.
Well, we started late. So
yeah, no, I just speed up that definitely. Yeah, so looking at this CP asymmetry with matter effect, the blue one actually here, what we have done, we have actually taken the standard CP phase. Of course, as I think I didn't have time to mention, the new fit value is giving some kind of a preferred delta CP, which is different from what I mentioned from NOVA and T2K, because they have taken the global fit. There are many other measurements. So they are giving some kind of a standard fit, like the normal order CP violating phase is giving like 232 degree. And similarly for the inverted ordering, it is giving 276 degree. So once we take these two values, then and plot the in case of dune standard model with Mather effect, the ACP actually gives a clear distinction between the normal ordering and inverted ordering. Similarly, in the right hand side, what we have done, we have actually done the same exercise for T2HK, as far as standard model is concerned with Mather effect. But although there is still some difference, not that dramatic difference, one can actually see a clear difference in the normal ordering and inverted ordering in case of dune. Okay. The same thing we did with that was the normal without. So once we include the dual NSI that just now I mentioned, we have included the NSI from epsilon E mu sector and epsilon E tau sector simultaneously. Once we do that, we can actually also see a clear distinction here. So for the same values of delta CP 232 for normal ordering and for delta CP equal to 276 in inverted ordering, there is a difference between the normal ordering and inverted ordering, which can be actually measured, and we can see some kind of hint of the mass ordering from these measurements. And as I said, like from the T2 HK sector, although there is a difference if you go to higher energy, but as I said at the beginning, the peak energy in T2HK is something like 0.6 GeV, which is at the like fast peak, as you can see. Although there is still a difference, but it may not be that relevant. But if you combine both T2HK and dune, maybe we can clearly say something on this. Okay, I think with this okay, the one more exercise we have also done. We have also done the CP asymmetry versus the previous two were basically the CP asymmetry versus energy. So if you vary the neutrino energy, what kind of the differences that one can see. Similarly, we can also do the same thing, ACP versus delta CP parameter, which we actually don't know. So that's what we have varied it from 0 to 2 pi, and we can see that the various ones in the blue ones is the standard model with normal ordering, and the green ones is the standard model with dual NSI and normal ordering. They are actually different from the inverted ordering, which are in the bottom plot, like the black and the red ones. So there is a clear difference between the normal ordering and the inverted ordering as far as ACP versus energy is concerned, or ACP versus delta CP is concerned. There is a clear distinction. And in the right hand side, we have the same plot for T2HK, but although there is some distinction, but they are actually not that much significant to be actually determined. So so that's what we find that looking at so once we get some indication of CP violating parameter, and we also make of course this will be difficult to measure ACP at this moment, but if we can measure ACP, and then we'll have a clear indication of the difference between the normal ordering and inverted ordering. Okay, so this brings to my outlook. There are many new experiments, and we expect more data and more several new results, maybe something new that we are going to see. As I said at the beginning, neutrinos will act as a pathways to physics beyond the standard model, as from the beginning of the discovery of oscillation. So we may get to see something new there. And leptonic CP violation will be crucial as far as understanding of the baryon asymmetry is concerned. And hopefully leptonic CP violation can be determined with, let's say, 5 years of running of T2HK and dune. So we can see clearly CP violation. Already T2K has already hinted that they have already hopefully seeing the CP violation in the leptonic sector, but not yet confirmed. And but NSI and sterile effects or any other neutrino non-physics, new physics effects can actually hamper these kind of predictions. So we have to better understand these effects, and it's an exciting time ahead in the neutrino physics. Thank you very much for your kind attention.
So yeah, thank you very much, Vincent. So we have time for questions. And maybe I start us off. So you mentioned that NSIs are important to understand for also especially then for those future experiments for Tune and T2 hyper K.
Yes.
So you showed at one point a plot where you basically looked at the how much it reduces the significance for that.
Yeah.
Are there ways to avoid that, or basically to distinguish NSIs and delta CP, or if by combining measurements or combining energy dependence, or?
So far, I don't think there is any. Yes, that will be an interesting thing to look at, but I don't think there is any effort in this direction just to, because there are conflicting ideas about the NSIs.
Mhm.
Also, so we don't have clear-cut idea how much NSI will be there.
Yes.
So once we know more or less like this much can contribute, maybe it will be possible to actually separate it from the CP evaluation sector. So we can say that maybe you can give say 10% error or something like that from NSI effect, something like that.
Okay.
But so far I have not seen
It's not-
any effort. Only thing that we are saying that yes, it is going to spoil the determination, but to what extent quantifying
It's not
is
completely
not
clear
yet.
yet.
Yeah, not
Okay,
yet.
so there's still more work
Yes,
required.
yes.
Other questions? Online? I have more. But maybe, okay, so one thing, so how does the energy dependence, okay, so there is a certain energy dependence for NSI and for delta CP, how the different parameters affect the oscillation
No,
probability?
for NSI, we are not taking any energy dependence because
it's basically just the effective
that's
operator.
that's the effective operator. The moment you have whatever new physics into play, that is defined.
Yeah, but how would it, so you basically, if you look at the different energies in the spectrum,
Yes. So these are
does the
probabilities.
NSI, in a
These are
probability?
probabilities. These are
Yeah.
probabilities. So either probabilities or maybe I have actually found the ACP parameter.
Yeah, but if I just look at the probability and the energy dependence of that probability,
Yes.
does the NSI and the delta CP, how do they enter there? Do they enter differently, or is there some? Okay, now it's the problem with the screen not
Suppose
working.
this is the one.
Yeah, that's probably.
So this is the probability versus energy.
Yes,
Let's
yes.
say. So probability versus energy, and also we have NSI into picture. Basically, in the right hand side, you can see the left-hand plot is without NSI.
Okay. So there is that uncertainty,
The
the
left-
functional uncertainty.
So this one is just standard model
Yes.
with matter effect, of course.
Yeah.
But the moment you invoke, of course, you see the clear difference.
Yes. Yeah.
Yeah. So the moment we know that what kind of percentage, to what extent NSI is affecting, we can actually distinguish from the probability.
Okay.
Yes. That's what you can see.
Okay. So there is in principle
Yes.
possibility to distinguish.
Yes.
Okay.
Because where it will cross and how much there will be the gap between this normal ordering and inverted ordering, or maybe for various values of delta CP, that also can be.
Okay. Okay. Good. Thanks. Other questions here in the room? I have more. So you mentioned there was that was I think quite interesting for me. So in order to get NOVA and T2K into agreement, you want to add that NSI of the 10% in epsilon E mu. But what are the constraints on that from are there other constraints on it? There should be other constraints, right? On those NSI parameters from meson decays or from coherent or some.
No,
that's
okay. So what here we have done, of course, independently people have considered like the NSI in the ice cube and coherent, all experiments people have done.
Yes.
But there is no global picture like the global neutrino data we have just table like that. There is no global kind of analysis for the NSIs coming from various experiments. But what we got, let's say up to 10% or so, is consistent with all other experiments.
Okay.
So
that's good. That's good.
Yeah.
That's what I want to hear.
That's what I want to hear. So So just to not to overdo or anything that we are seeing anything significant, no. This is consistent with the similar experiment from IceCube and other. So, but actually, what will be the percentage that we don't know right now?
Yes.
So,
But do you need coupling specifically, let's say, to electrons or up quarks or down quarks? Or here it's now, of course, all together.
yeah. Actually, I think I didn't stress too much. If you remember, I have actually given. You can see that the effective coupling that we are taking here actually is coming from all of them. The epsilon alpha beta is epsilon E alpha beta electron type and 3 times up quark type and 3 times.
Okay, okay. So there is not distinguish.
There is no distinction between this. It's an effective coupling.
Yes.
But if there will be, I mean, to go into quark level and distinguish NSI will be very, very difficult. I don't know how to do that. But effectively, if it is coming, then they will contribute to this parameter epsilon alpha. Yes. So we have collectively taken, but maybe in future there will be some effort to do in some experiment. But how do you do that? You have to have.
You would have to compare with different proton to neutron ratios.
Exactly. Otherwise, it will be not so easy. Yeah. But yes, maybe one can actually get some idea.
Yeah. Okay. So I would say so are there more questions online? No. All quiet online. So yeah, then let's thank Anshan very much for